Mixed exercise 7.01 is an application of forces. A-level applied maths, mechanics, year 2. We've got 2 questions. Question 1. A uniform rod AB of mass 20 kilograms and length 4 meters rests with one end A on a rough horizontal ground. The rod is held in limiting equilibrium at an angle theta to the horizontal, where theta is equal to 3/4 by a force acting at B, as shown in the diagram. The line of action of this force lies in the vertical plane, which contains the rod. The coefficient of friction between the ground and the rod is half. Find the magnitude of the normal reaction of the ground on the rod. First, there are some forces acting on the rod, and we need to draw them. So the first one will be the weight of the rod. And this will act at the center because the rod is modeled as uniform. There's also a normal reaction force, R, due to the rough ground. And this will be perpendicular to the ground. The ground, we are told, is rough. That means friction will act. If the rod is to slip, it will slip in this direction. And that means friction will act in the opposite direction. So let's put that one in as well and label that F. So these are all the forces acting on the rod. You will probably notice that there's not enough information about this force holding the rod in position. We do not have the magnitude, neither do we have the direction. The direction could have been its angle of inclination, either to the rod or to the horizontal, or even to the vertical. But none of these is given. So the best way forward in solving this problem is to eliminate this force in your calculation. And to eliminate this force, we need to take moments about B, because the perpendicular distance of the line of action of this force from B will be 0. And so this is one question where we have no choice as to where to take moments. So we're going to take moments about B. We need to now decide which of the forces will produce a clockwise moment and an anti-clockwise moment. First, we notice that taking moments about B, the normal reaction force R will produce a clockwise moment. And then the 20 G-Newton force will produce an anti-clockwise moment. So will the frictional force F produce an anti-clockwise moment. So now we know the senses of the moments we're going to take. So we need to now calculate the respective perpendicular distances of these forces about B. It will be easier if you draw a horizontal line through B parallel to the ground as follows. In that case, this angle here and that angle will be alternate angles. And so this angle becomes theta. Now the line of action of R will be perpendicular to the line we've just drawn as follows. So the moments due to R will be this force times this distance. But this distance is 4 cos theta. And that is resolving this length here along this line. In the same way, the line of action of this force will be perpendicular to the horizontal line that we drew. Now this distance here, from this point to that point, is 2. Because we know that this is acting at the center of the rod. And the whole length of the rod is 4 meters. So that makes this length 2. And that means this length will be 2 cos theta. Now we need to find the perpendicular distance of this force from B. And so we put in the line of action of the force. We can clearly see that the perpendicular distance will be this way. And that would be 4 sine theta. And that will be resolving the length of the rod along this line. So we now have all our perpendicular distances of the forces. We are ready now to take moments and write our equation down. So the principle is this. The total anti-clockwise moment will be equal to the total clockwise moment. And so now let's taking moments about B. So taking moment about B, I will have R times 4 cos theta is equal to 20G times 2 cos theta plus F times 4 sine theta. But we are told that tan theta is equal to 3 over 4. So if I draw a right angle triangle and put theta over here, I can put 3 here and 4 over there using SOHCAHTOA, and that means I can use Pythagoras theorem to calculate the length of the hypotenuse, which will be 5. So I can use this triangle to write down the exact values of sine theta and cos theta. And sine theta will be 3 over 5 and cos theta will be 4 over 5. So I can now replace cos theta and sine theta in this equation with the exact values over here. So if I do that, I'm going to get R times 4 times 4 over 5 is equal to 20G times 2 times 4 over 5 plus F times 4 times 3 over 5. So 5 goes here 1, 5 goes over there 4. So the whole equation can now be reduced to 16 over 5 R is equal to 32 G plus 12 over 5 F. But we also know that F is equal to mu times the normal reaction. So F is equal to mu R, but mu is a half, and that means F is half times R. So I can replace F in this equation with half R. If I do that, I'm going to get 16 over 5 R is equal to 32 G plus 12 over 5 times half R. Now, 2 goes here, 1, and 2 goes to 6. So the equation reduces to 16 over 5 R equals to 32 G plus 6 over 5 R. I can now rearrange to make R a subject. If I do that, I'm going to get 16 over 5 R minus 6 over 5 R equals to 32 G. But 16 over 5R minus 6 over 5R will give us 2R. And so I get 2R equals to 32 G. And so R is equal to 32 G over 2. And hence R is equals to 16 G newtons, which is also the same as 157 newtons. And this is the required value of the normal reaction of the ground on the road. Question 2. A ladder of length 5 meters and mass 18 kilograms has one end A resting on a rough horizontal ground and its other end C resting against a smooth wall. The ladder lies in a vertical plane perpendicular to the wall and makes an angle beta with the horizontal ground, where tan beta is equal to 4 over 3, as shown in the diagram. The coefficient of friction between the ladder and the ground is mu. A man of mass 60 kilograms stands on the ladder at a point B, where AB is equal to 3 meters. The ladder is on the point of slipping. The ladder is modeled as a uniform rod and a man as a particle. Find the value of mu. So we need to put all the forces acting on the ladder in. The first one is the 18 G Newton weight of the ladder. And this will act at the center of the ladder. And that makes the distance from A to this point 2.5 meters. We'll need that later in our calculation. There's also the weight of the man, which is 60 G Newtons, acting at B. And there is a normal reaction force R due to the rough ground. The ground is rough, and that means there will be friction acting if the rod slips. And if the rod slips, to slip down the wall, and means it will travel in this direction. It follows that the frictional force will be acting in the opposite direction. So we can put that one in and label that F. The wall is a smooth wall, so there will be no frictional force along the wall, but there will be a normal reaction, which we can call S. And this force will be perpendicular to the wall. So we've got all the forces now acting on the ladder. So at this point, we are going to take moments, and I'll take moments about A. So taking moments about A, you can see that the 18 G Newton force will produce a clockwise moment about A. And so will the 60 G Newton force. And the normal reaction of the wall on the ladder will produce an anti-clockwise moment. So now we know the senses of the moments that we're going to take. We need the respective perpendicular distances of the forces from A. The line of action of S is perpendicular to the wall. And so its perpendicular distance from A will be this distance here, which will be equal to the distance from C to this point. And that will be 5 sine beta, which will be the resolution of the length of the rod along this length. In the same way, the perpendicular distance of the 18 G Newton force will be 2.5 cos beta, and that will be the resolution of this length along the ground. Similarly, the perpendicular distance of the 60 G Newton force will be 3 cos beta. So we can now take our moments about A. So taking moments about A, I will have S times 5 sine beta is equal to 18 G times 2.5 cos beta plus 60 G times 3 cos beta. So I can simplify this equation to get S times 5 sine beta is equal to 45 G cos beta plus 180 G cos beta. If I divide every term by 5, the equation simplifies to S times sine beta is equal to 9 G cos beta plus 36 G cos beta. But 9G cos beta plus 36G cos beta is equal to 45G cos beta. So the equation becomes S times sine beta is equal to 45G cos beta. So at this point, we can also resolve the forces horizontally and vertically. So resolving horizontally, I'm going to get S is equal to the frictional force, F, because these are the only two forces acting horizontally and they are acting in opposite directions. So it means S is equal to F. If I resolve vertically, I have one force going upwards and two of them coming downwards. So it means R will be equal to 18G plus 60G. And so resolving vertically, I'll have R equals to 18G plus 60G. And that will give us R equals to 78G. But we also know that F is equals to mu R. This equation implies that S equals to mu R, since S is equals to F. But R is 78G, so it means S is equals to 78G times mu. I can now replace S in this equation with 78G times mu. And so if I do that, I'm going to get 78G times mu times sine beta is equals to 45G cos beta. So I can divide both sides of the equation by G, and so that means G and G will go, and the equation becomes 78 mu sine beta is equals to 45 cos beta. I can now rearrange this equation here to make mu the subject. So if I do that, I'm going to get mu is equals to 45 over 78 times cos beta over sine beta. But for pure maths, we know that cos beta over sine beta is equals to cot beta. And so mu becomes 45 over 78 will reduce to 15 over 26. So that will be 15 over 26 times. And as already stated, cos beta over sine beta is cot beta. So that's cot beta. But cot beta is equals to 1 over tan beta. So we know that cot beta is equals to 1 over tan beta, which will be equals to 3 over 4, because tan beta is 4 over 3. And so mu becomes 15 over 26 times 3 over 4. And that will give me 45 over 106. And so evaluating that will give us mu is equals to 0.43, and that is the required value of mu. And this brings us to the end of this session on application of forces. Mixed exercise 0.01.